So basically kind of a machine learning 101, starting with the regression models. Any questions? Yeah, so this is just there used to be this is the book that used to be very like everyone was reaching out to this book back in the day. Even the time for it's still a very good book, like the pattern recognition machine learning by Christopher Bishop is still a good book. But and then even I myself like 10 years ago when I was trying to really because I'm not a computer scientist by like degree. So I've taken a lot of those courses. So there was this course by Andrew. No, this is NG Yang, whatever. NG. So this used to be a very good source of material. Like I myself started listening to those courses. It's now almost 9 years. Yeah, 2014 was the time that I even myself decided to switch here. I was doing stuff more in the signal processing, communication. That's like a double E for those of you who either may have a double E. This is I had a very double E focus. I still writing code, a firmware code, but then I decided to switch. This was the I don't know if this was exactly this Stanford course, but he used to have a lot of good material, which is still there, I think, machine learning. The first version was on Octave. So Octave is just the free version of MATLAB. And so you can tell how far it was. But that was like 2014, end of 2014, the beginning of 2015, where I was really started listening to those, just to organize my understanding of machine learning. So these are derived from that, but nowadays you can find them on any YouTube video. So. And again, this was covered, most of it for you guys on, I think, 6010 and 6050. So this is going to be just a recap, but from a different angle. So I figure since most of you have those slides, let's just kind of refresh the just content. So we are going to talk about regression in the first part, linear regression, the continuous version, right? And then we are going to talk about the digital version, discrete version, which is logistic regression in the second part. And these are the first basic machine learning models. Put K and N aside, K-nearest neighbor that we talked about last week. This is just that was not really machine learning models. These are the two very first basic machine learning models. It gives a good understanding of stuff. What do we mean by metrics? How do we fit, overfit, stuff like that? And well, it's a line, right? Ultimately, you can say this is a line if you have one feature in mind. Okay? Okay. So, yeah. This is the, these are the notions that, like, again, very, at this point, should be repetitive for you. We have a number in mathematics called scalar. Bunch of numbers tied together for whatever reason are called vector, and then you have a matrix. We normally use capital for matrices. And the reason we use that is that if you want to multiply a lot of numbers, like a neural nets or whatever, you better have a matrix kind of a foundation to just multiply a lot of numbers by each other or transpose a vector or stuff like that. Okay, so just again to give you an idea, this is a good kind of a neck-to-neck comparison. Assuming that you have one feature, okay, just assuming we have one feature. A pair of data, x1, y1, these are just your data that you have collected. Think of x as anything and y is a function of x. The goal is try to learn a function. So this simplified the whole machine learning in one slide. the whole goal of everything is to find the optimal function that gets x and gives you f of x, which is as close as possible to y, right? If y is categorical, I mean, now think about y. If y is categorical, you are solving a classification problem, whatever classification problem. And again, I feel like we're doing backwards stuff. This would be like a very first, at least three courses back, but just a repetition. And if y is a real value, you are solving a regression problem. So as I repeated many times, most of the problems that you have solved, decision trees, SVMs, neural nets, they are all capable of being a classification problem and or a regression problem. You can do both. Basically, it's just, you can design both with the same architecture. At the very end, you decide to take a real valued number or a 0-1 number. Okay, that's just a decision you make at the very end, which would change stuff, but that's a very decision at the end. And yeah, so if you're coming from a statistical background, and yeah, one thing that is different between today's session and maybe 60-10 is that has a heavy statistical weight to that. This I'll try to make it more machine learning than statistics. The two can really talk. So looking at a regression problem, should be very familiar for anyone. There are a bunch of data that you have collected, y versus x, and then you fit a line to that. It's the simplest line. It's a simple linear regression problem that you're trying to solve today. On the left side, you are trying, you see, like the data looks very similar, right? But you don't care about the value of y here. There is a y here, right? There is always a y here, but you care about which class this sample belongs to. You don't care about the value of it. It's still, it may have a value 0, 1, 2, 3, red, blue, green, but you care about which class it belongs to, and then you try to find a line, whatever line, that separates these two as much as possible. So the error here is simple, right? The error here is just the delta between the actual y and the predicted y. The error here is slightly complicated, but you can say the error here is the number of blues that are classified as green and the number of greens that are misclassified as blue. Right? That's just, there is some notion of error. Okay. But this is the f of x, and this is kind of like an f of x. But the way you do it is that you use this f of x directly, right? When you fit this line, you'd go out to say, this is my f of x, use it. And you train this f of x, you would not use it directly. You would say, okay, calculate f of x. If it's above a certain number, it's blue. If it's below a certain number, it's green. So you see, you're solving a very similar problem in both of them. Making it a regression classification is a very last layer type of decision that you make. Okay? Okay, let's start with a simple linear regression problem that we have gone through. We're trying to find, and simple linear regression is that there is no nonlinearity, it's a simple line. It's trying to find the best straight line to take the data. And we talked about it. You have an independent, y is independent, sorry, x is independent, y is dependent. And well, what the best line is a question to be answered. What is the best line? But the goal here is to find the line that you can use for future predictions. The best thing is still remain to be answered. So remember, we had a lot of these examples back in that 60-10 and 60-15 course. You are trying to predict the house price of a house, given the square footage, right? Probably, yeah. There is some, linear. There is some proportionality. It's not used linear or non-linear. There's a, as obviously the house increases in size, it would increase the price of the house. So let's see if we can treat this as a regression problem. So because we are doing a simple linear regression, all you can do is to multiply some number by x, which is the square footage plus b, okay? If we call y your prediction or dependent variable, we call this w weight. In this case, it's the slope. The b is intercept or bias. So you're basically trying to predict this w and b. And if you remember, we always had a hypothesis, right? We are assuming this is the best thing that we can do. All right, so I think we talked about this before, but look at this data space. We have a bunch of lines, a green line, which is flat, right? So in the green line, W is 0. Okay. We have a red line, and let's call this a yellow line. And what you have on the other side is just a W and B. Okay. Well, let's start simple. What's the problem with green line?
Points.
Well, let's just elevate it a bit. Then what's the problem with green line?
There is no angle.
Huh?
The green line, there is no angle. It's just,
Well, what is the problem? Yeah, I know. You're describing it. You're not telling me what's the problem with it.
Underfit.
What?
Something underfit.
It's underfit. It's a heavily biased model. You see, it's talking about prejudice and bias. That's it. Whatever the footage of the house, square footage, it says, okay, I'm gonna say $1.5 million. By the way, if you're living at the, you can get into construction business. From it, right after medians. If you want to make money, you can get into construction business. Think about it. Okay. So okay, the green line is underfit and it has a heavy bias. What is the problem, or which one? Not a problem. Which one between the red and the yellow line is better?
The red one is better, and
Do you know that?
because I think the yellow one is kind of like overpaid. I forgot actually. If we want to follow baseline, because looks like
Because your underfit guess worked.
no.
That doesn't mean you're overfit. Later.
Okay, I'm not sure.
Well, so I think we played this game before. You shouldn't really respond to the question. Yeah, the red line looks closer to somebody, but the idea is, okay, what metric you are?
This is the data point.
What is our matrix? What is our metric?
The distance between the points into the line.
Squared.
Squared. Yeah.
Sum of the square. That's basically the popular metric. So the question is, what is even a metric? But a question that we never ask. I know there's a common sense in your mind. What metric you're maybe I design a metric that even the green line become the bear. So yes, there is a common sense in all of your mind, but the question should be, what is the metric we are considering as a best fit? So you all know that we can define error as the delta between the prediction and the observed value. These are the errors. And the common metric here is called mean squared error. It basically says that you'll take the difference between the prediction and the observed to the power 2, And then you have to sum it over, or basically, how you get to the optimal, there is a mathematics here, and if I definitely encourage you guys to listen to that video by Andrew, because it would tell you what are the optimal, how can you get, so basically it solves this simple problem. And I think it's worth at least solving this problem for once. So you define, and that's the process, you define a metric for error. First, you have to define how do I measure the error. Okay. Then you have to define, based on the error, you have to define a loss function. It is very mathematical, so just bear with me once, because I think it is always interesting to know how do you really calculate these two. How does computer calculate this W and B? How does it do that? It defines a cost function using the error that you have already defined. So you have defined this as your error. This gives you a cost function. A cost function is just the sum of the error on all the points. How many points do you have? You have n number of points. So you have to sum all the errors that you make. And that's your cost function. But the cost function, this is a very simple case. You can really write it. You cannot really write the cost function in most of the cases that you have. So this happens to be WXI plus B minus YI squared. Okay. Before getting into more depth here, is this clear what this function is? You have n number of points. So your goal is to find W and B. You have n number of points. For each point, you can, there is a, you have this, these are already your sample data, right? Your data is X1, Y1, X2, Y2, all the way to Xn, Y. So n data. You just sum them up like this. This is the cost function. So the goal here is to find the best W and B that would minimize the cost function. So you know how do we do this step?
Differentiation.
Differentiation. How much you guys are familiar with differentiation? So this is I mean, again, normally let me see what I have. I have some stuff here, but I wouldn't go through. It is worth, if you are going to live in, make money out of this domain, you better at least do one of these differentiation once in your life. I would really encourage you to do that. Because I'll try to explain this today to the best extent. But if you don't understand how these models are trained, you may still be able to do the job. I'm not saying you won't be able to do it, but it's worth understanding these slight mathematical, it's not slight, it's a little bit, but this idea behind the differentiation. So let me just kind of look at it again. You have a lot of data points. You have a hypothesis. Again, this was your hypothesis to go and fit a simple line. You have to define an error function and then a cost function and then minimize this. So you should find a W and B that minimizes this. Okay. But let's just take a simple case. Because you are looking at, let's say, a W and B, this is if you plot this in terms of W and B, okay, if you manage to plot this J of W and B versus W and B, so it's a 3D shape. Okay, just to give you an idea, do you know why it called X squared? How does it look like? It's like this, right?
No shape.
So it's a convex curve. And every convex curve has a minimum, or a concave curve has a maximum. So it's easy to say that what the computer does. So how would you do it from a non-mathematical way? You just have to put all the possible W and B and see when it gets really to an optimal point, which takes a long time. There are ways, like gradient descent, that you probably hear in machine learning slide, that would optimize this process. Okay, so basically, if I tell you find the minimum of this curve, you have two ways. You either have to take the differentiation of this, x equal to 0, give you x equals 0, and boom, you find the optimal point. Or you have to put all the x's that you can think of with some resolution and find the optimal point, which actually the computer does that. There's something in the middle that say, hey, okay, find the slope of this and move towards. So it kind of moves back and forth all the way to it gets to this optimal point. That's how the gradient descent works. You probably can do the same thing. So you would neither try all the points here, nor the problem is so easy all the time that you can take the differentiation on the paper. It's somewhere in the middle, and you have to do something like this to get to that semi-optimal. It does that for decision trees, SVMs, logistic regression, neural nets. They all work in the same fashion so that you can find the optimal point where this cost function is minimized. If you go now to a heavy machine learning course, like from scratch, they would spend obviously a sheer amount of time on this topic, on the mathematical part. I'm not saying get involved fully in that, but I say it is worth understanding this, at least the basic case for one of this very simple case. So this is talking about how you try to find the optimal point versus W and B, somewhere in the middle. And in a way, the way it does that is that it goes to this, let's say it starts from this line that is obviously not optimal and gets to the optimal point after a couple of training rounds. So this is equivalent to J being here. It's not 0, 0, right? You're looking at a 0, 0 type of a thing. 0 in terms of value. Think of a 3D thing. You're trying to find when this is really minimized, the minimum value. So it's going to be something like this. This is the process. The process that goes is called the gradient descent. So it basically, the way it does that is I can kind of explain this here. When you're trying to do this here, it says, okay, let's start with some random point. And okay, what is the slope here? The slope here is, let's say, 2x. Okay, give me some other point, and it gives you here. You may overshoot here, but ultimately, again, like this, you would reach to the point that you're in. This is also like this is called gradient descent. It is basically trying to minimize this for complicated cases without really taking the differentiation. You can still, let me just do that. You can do the derivative that we talked about. You can take the derivative with respect to W and set it equal to 0. And you can take the derivative with respect to b and set it equal to 0. And then this gives you the optimal W and P. This is the mathematical way of doing it. Instead, they have developed this gradient descent, which uses this notion. But because the cases can get very complicated, you cannot really solve this if you have x1, x2, x3. If you have multiple x's, then solving this becomes a huge problem. So it does, and this is called gradient descent. Questions? So, just to wrap up what you just said, you're trying to minimize a cost function. In the analytical solution, you take the derivative of the function, right? You say 0.2. So you either find some critical points that if you can plot the function, which you cannot do, and the number grows. The number of features grows. If you have 10 features, then you cannot do that. But if you were able to really plot this J, you can say, hey, go to the minimals. That's where I want to be. And then what are the W's for that? The numerical solutions is what we really use in the computeric way of doing stuff, and then gradient descent happens to be still one of the fastest approach to find. The idea again here is to find. Forget that. Let's assume this is a function of W and B. These are fixed, right? You have X, I, and Y. They're given to you. You are trying to find the minimum of this function. Think of that in a 2D space, right? Why? Because a 3D space, because we have W and B, and J is your value, right? So it looks like this. W and B, and this is your J. Think of a plane in this space, and you're trying to find a minimum of J for these two. There should be a W and B that this is minimized. Now, if you have W1, W2, W3, then just imagination of this becomes even harder. But the goal here is to find the W and B. And if you have multiple W's, then all the W's, there's a pair of W1, W2, W3, and B that minimizes this. Again, this is not always the case because sometimes the functions are not really convex. So not every problem has a solution, but simple problem have a minimum, have a global minimum. Okay, I put that in. I found that in. Then talk about gradient descent algorithm. Whenever you think it's out of the your scope of imagination, and just let me know. Okay. Okay, so just repeating stuff. We are trying to minimize a function of two. This is a very simple case, W and D. One variable, one parameter. Meaning one input, so you need a slope and you need an intercept. And just written there. We are going to explain in the next few slides the gradient descent algorithm, which is an iterative algorithm, meaning it's in multiple steps. It starts from a random point and gradually decreases the J to a certain point. Then where do you stop? When J doesn't really change. Okay, let's just try. So the visual part of it, again, you can also find that in the video, is that you start, this is a good visualization, a hyperplane of WM. You start in some random point, and it looks like that you can think that there sometimes are two optimal. But the gradient descent algorithm follows this path. So if you're doing a good job, you wouldn't try all of this. It takes a huge amount of time. You're going to try a very few points until you reach the optimal point. There exists an algorithm, which is called gradient descent. The job of gradient descent is to help you not try all of these points to find the minimum, but to follow a path to get to the minimum much faster. You may have multiple optimal points. It is possible that you start from here and you get to this one. You start from here and get to this one. These are minor things. Now let's understand, and again, in order for us to understand this, we should be familiar with what do we mean by this derivative of J with respect to W and derivative of J with respect to B. Who knows this? Who doesn't? Let's see if I have something. Because we need to be, this kind of assumes that you know what is this. Okay, let's take a moment here and at least compute that.
The rate of change of J when each W.
Yeah, that's actually a good interpretation. It's the rate of change of J when W changes. So let's start with some simple cases. Some simple cases here. Do you know what is the F, the X?
4x to the power 3.
4x to the power of 3. Who doesn't know? Who does know? Because just show of hands, who doesn't know? You know that?
Partially, I remember a little bit about it.
No.
Cos x df by.
So why do you know this one? You didn't know the previous one.
I just saw the effects thing. I
Okay, so let's, you know, you can go to a table. Let's let's take a different approach. This is the part that I actually failed in teaching. I need to make this better because, yeah, I keep failing this. Okay, let's forget that there's some formula, but let's go to the explanation that you said. This means that if you change X by 1 unit, okay, or 2 units, what would happen? How much F would change? Right, and the change is okay. Think of this as, you know, a function, obviously, and it's obviously it looks like that if you change it by 2 units, of course, from which point, but if you change it by small amounts, how much F would change? That's the derivative. The idea of derivative is to tell you how much J would change with small changes in W and in B. Okay, that's okay. That's fair, and I think we don't need to go further. There are then tables that you can go out there and find how you compute the derivative of a function and a function can have multiple variables, right? So this example, it has only 1 variable. In this example, it has 2 variables. Okay, so let's assume that there is this function, there is this number that is given to you, which shows the change of J with respect to W. Small changes in W and small changes in B, okay? Now, we all know that when this number is positive, it's an ascending kind of line. Again, it could be non-linear, right? It's not, it could be like this, right? It could be like this, it could be like that, but it's ascending anyways, right? Concave, convex, or line. And when this number is negative, it's a decreasing fashion, right? That's also a good thing, right? Good job creating those slides. I haven't made those. So what you want to know is that let's for a sec, let's assume there's only W, no B. Okay, and let's say you cannot, for whatever reason, do this calculation of 4x to the power of 3, because if you can do that, problem solved. But let me take it back. You can do that, but you can still not find the optimal point, because here's the thing. I'll try to organize this in a bit. Let's go to a slightly more complicated function. x4 plus 5x cubed. What is the derivative of this with respect to x? 4x cubed plus 10x.
Plus 10x.
Okay, and what is the minimum of x, f of x? What is the minimum of f of x? For which value of x, f of x is the minimum?
0.
Yeah, you know, how do you calculate this?
So I think now it's the whole value is 0. You can derive it one more time.
So what you do is that you take the first derivative, you put it equal 0. If you can solve this, it gives you the x for which you are either maximum or minimum. Okay? So we can take the derivative, but it's hard to put it to 0. It's hard to solve it for that, for J. So we can take the derivative, we can always take the derivative of functions using the methods that you can search for. But it's not as easy as this one to put it to equal to 0 and solve it. Otherwise, you can find the minimum, right? If you can, so you do this, then you cannot mathematically solve it quickly. Otherwise, it would solve it quickly. So you take the derivative, and you are trying to, step by step, using gradient descent, find the minimum or maximum of this curve. What you do is simple. You take the derivative. You start from a W, okay? Again, let's think that you only have J as a function of W. And J is like this. And let's say you at each point you can find the derivative, but you cannot fully solve the problem like this. Is it clear? So what you do is you take the gradient descent. Gradient descent says that, okay, take a random W, and find the slope of the J at that point. So it's like 4x3 here, right? 4x3 plus 10x. No equal to 0. If you start from x equal 1, this is going to be 14. Put that here. Choose a number eta equal 0.1. This is called learning rate. It's fixed for now. The next W, you are going to choose the second W, right? Either here or here or here, right? The next W is the current W minus this fixed number times the slope of W at that point, W current with respect to J. Is it clear what we are doing? We choose a random point. Because it's a function, you can take the derivative, put that W inside, it gives you a number. Assume this is 0.1 for now. The next W is going to be the current W minus 0.1 times the slope. What does it mean? Let's assume this number is positive. So it means that you are kind of like here, right? That you are in the positive slope. So it tells you to reduce the W. The next W is going to be smaller than the current W because this number is positive. And vice versa. If you're on the negative slope, this is going to be positive. So the next W is going to be larger than the current W. Yeah, this is a harder case, but if your cases look like this, you can think of this, right? It's going to be like this. Something like that. It should happen, right? And then at some point, your W is not changing. If the W current and next are not changing a lot, stop. What is the problem? Or okay, you can imagine that it would solve this for the simple case of one minimum, right?
Mhm.
In this case, it may just lock here, get locked, and yeah. Okay, so what I was trying to do here, I was trying to explain the numerical way of finding the minimum of a function using gradients. So they use gradient descent in, again, logistic regression, SVMs, decision trees, all the way to neural nets. They all work based on this notion of finding the minimum using a stepwise approach called gradient descent.
Is there any other?
There are there are so there are other approaches. So the gradient descent are not also flavors, but this is I think the most powerful one.
Yeah, I'm not sure, like, for the hyperplane there, when there's a multiple minimum, how did the
You may get to any other.
but then, like, if one minimum is lower than the other.
You are forget about the hyperplane. That's why I put it here. Single variable. This is two variable, harder to. In the single case, in this case of multiple minimums, you may get trapped here and pick this as the minimum.
And that is
a bad thing to happen. It will happen.
it will happen.
So the thing is, that's why you have to do that. There are other ways to get out of this, but this is a convex problem. It's not a convex problem. Oh, this is getting very hard. I'm not going to get there, but there's a convex problem and there's a set of non-convex problems. Convex problem, you are guaranteed to get to the minimum using gradient descent. Non-convex problem, you're not guaranteed to get to the minimum. What you do is that you start from another random point. So you try this not once, 10 times. Different, these are random points, yeah. So they're going to be different. Yeah. In hyperplanes, these are non-convex problems.
So here, when we try to minimize the cost function, in this case, we are getting like different values of W, but probably the value of B is the same.
No. Okay, I'll explain this, yeah. At every step, you do it for W and B together.
Okay.
That's actually a good sign of listening. No, that's a good sign. So you do this for both of them at the same time. You do this for W and B. Basically, you get a W, B next, a pair of next numbers. Until convergence. What you see in the bottom part is that this is the derivative of J with respect to W. You see it becomes 2 times this guy times X. Because with respect to W, this becomes a coefficient. Remember that? So what you see here is the derivative of W with respect to derivative of J with respect to W. This is the derivative of J with respect to B. That's why these two are different. So if you don't know why this is like this and this is like that, then you need to take a course on derivatives. But this is how you numerically get to the optimal point. And there you see there is this learning rate eta here that can play some role. Okay, so if eta, think of a single dimension now. It's easier to think of a single. If eta is very small, what was eta? Eta was the number that you would multiply by the slope to subtract from the current. If eta is very small, it takes you forever to get to this point because you go slowly. You can make eta 0.0001. If eta is very large, you may jump from the negative slope to the positive slope, you overshoot. There is an optimal eta, but that's also a hyperparameter. Remember those hyperparameters? One of them is now eta. So if eta is very low, it takes you a long time to converge. If eta is very high, you wander around the optimal point of it. So it still converge normally. Okay. So if you have more than one variable, number of bedrooms, number of floors, age of home, I'm getting sick of this example. But you can make money if you go to construction. Why don't you guys go to construction? Starting from our comedian in the class. Have you give it a thought? Huh? You can be realtors if you don't like it too much of a heavy work.
The California weather is good for construction.
It
You can't complain about that.
Yeah. So the difference between this one and what you had before is that you have multiple features. That's it. So what is going to be different is that I'll kind of try to skip forward. But the difference, let me go back because I would have done it differently. Is that now you have, if you have a W1, W2, W3, W4. So you have multiple, you're in an n-dimensional space. You're not in a two-dimensional space or three-dimensional space. So for the case of multiple linear regression, you have a, again, you have a feature x0, x1, x2. And then what is trying to explain here with Ivan, that obviously you have multiple W's in your gradient descent algorithm. There is an analytical solution next to gradient descent that sometimes we can do this one. It's not all the time, but you can do this. In the analytical solution, you have to use this notion of matrices and vectors and all that. So you put all of your features here, your target variable and your weights. So you put the weights into W, a vector of W's. Your target variable in a vector, one vector of all the target variables. And because you have basically for each sample point, you have a xi0, xi1, xi2, xim. So you have m feature, right, and n data point. So you basically create this big vector x. So x here is a matrix. It's basically like this. Let me write this so that it wouldn't be like a easy to tune that. It's just what is x? This big X is x1 transpose, x2 transpose, all the way to xn transpose. So it's basically like this. It's x1, xi is this guy. So it's going to be x1 0, or I think, yeah, x1 0, x1 1, all the way to x1
And
n. Right. So what is this? What is this? This is your first sample. In the house example, number of bedrooms for the first house, number of bathrooms, square footage, whatever. Second house. We put them all in one, and this is x. And so these are the number of samples. These are number of features. Right? You can put them in this big X. It's obvious that X times W equal Y, right? So luckily for this specific case, if you manage to inverse the matrix, the solution is this. For this specific case, there's a closed, this is called closed form. You don't need to do gradient descent. You can simply do, this is actually not simple, but if you are managed to do this, these are all numbers, it gives you the W right away. There are certain conditions under which you can do this. This is called normal equation. Closed form meaning that you don't do numerical. Again, approaches like gradient descent are numerical, that you try until you get to the solution. Approaches that gives you the answer right away, like our exact derivation and equal 0. This gives you closed form. Closed form, if you can get the closed form, which you are not 90% of the time able to do that, it gives you the right and definite answer of the box. Yeah, and you can just refer to the slide later. All right, let's take a break. After 10, 12 years of teaching this, it's still a heavy thing to teach.
Very hard. That's hard, actually.
Yeah.
I did read the PPT, but I still don't understand.
You what?
I mean, I did read this PPT, but I still don't understand.
The problem is that the problem is that when I was looking at this for the first time, just 20 years ago, I had already taken 10 courses on derivation, integral, convex problem. So this was not a hard thing to look at. But you guys will, unfortunately, or whatever, you are given this without the required background. That's the problem.
Yeah, that's true, actually.
Sir, in my case, I did solve all these derivatives long back ago. And I still remember, but I can't relate this to, computation. 2 classes in summer.
Let's go. So
Let's go down.
just that I have
就在哥大前
covered 40 out of 70. I have that, but I'll try to speed up so that I can get to the latest equation. So the part that, okay, after talking about how we solve the problem, which is not what we covered in the previous courses, at least the gradient descent, let's talk about the model. This we covered. So you're using 5 different matrices. The one that talked about is mean squared error, which is basically you take the square error and then you average them. But you can use absolute error, which is just not squaring it. Or you can take the square, but then take the root of it. We have R squared and adjusted R squared. Let's briefly talk about them. So mean absolute error is clear, right? You take the delta between the observed and the target, but you just don't power it to the 2. Mean square and roots mean square, right? You can, this definitely gives you different lines if you divide it. Lines should be, in the example of one dimension, the lines should be very close to each other. But this should lead to different, so when we say which is the best line, and the answer is, okay, which of the lines, what is our metric of evaluation?
Professor,
Yes.
is there a reason why we prefer the mean squared over the others? Like we don't really.
So, yeah, there is, so basically what this does, you can kind of guess, right? This is penalizing the error more than the other. Right, this is penalizing the error more than this one. I'll give you a different perspective of it. Sometimes you're solving a problem and this gives you better result than this one or vice versa. Better result meaning that you can see that your predictions are better if you use that metric. Again, it might not be the best solution, but from a problem standpoint, but depending on how much you want to penalize, you may use between this one. In other words, there's when we want to kind of ignore the outliers, we may try this one. Because this is going to punish the outliers. And this is somewhere in the middle of these two. Okay. So the next thing is, okay, do we have a nonlinear version of it, right? So far we have W0 plus W1x. But what if the problem is not even linear? Then you need to inject nonlinearity in your model. The simple way to inject nonlinearity in your model is to use x squared. That's a simple nonlinear model. So the nonlinearity, obviously there's no limit to that. You can go to polynomial. So look at that, like if you want to really fit something to blue lines, like a sinus or cosine, you obviously need to go to the third degree of polynomiality. Otherwise, you cannot capture a good fit on the blue line, blue dots. So just to give you what happens, if you go with, a flat line, totally over biased line, under fit. If you go with a 1 degree, go with 2 degree, you go with 1, and then you all the way to 3, that's what it gives you. If you go with 9, you're gonna overfit. You can capture, but you're gonna overfit. Obviously, you're very far from a hypothetical green line. So you can go from an underfit to an overfit. An overfit is a very simple model that does not capture anything, almost it's just a bias. Or again, these are even not, there's a spectrum, right? You go from a very underfit to a very overfit model. The overfit model is complex, fits very well on the training data, but it does poorly on the test data. Okay? So that gives us this kind of a notion of like, okay, what is the, and this again, we talked about it in length on different courses. On an underfit model, you have a very high bias. You have small number of features, and the model performs poorly both on train and test. On the very right, you have an overfit model, which has a high variance, has a lot of features, unnecessarily high features. It does a very good job on train set, but does very poor on the test set. And there is some point in the middle. Always there is a point in the middle. So as you increase the degree of your model from 1 to 4 to 15, you would notice that you are going to the overfit domain. That's why this is a very kind of interesting curve. When you are spotting the error versus the complexity of the model. Again, this has nothing to do with regression, but with any model. You can define a complexity of the model. Any parameter that tends to make the model more complicated is one of the parameters that you can use on the x-axis. You are reducing the bias and increasing the variance, which is just another way of saying you're going from an underfit to an overfit situation. But you are not decreasing the error all the way. You are decreasing the error. Again, this is the error. The black line is the error. So the black line is the only error. The other two are various. Is the error, let's say, on the test set, not the train, obviously. You are, as you make the model more complex, you are decreasing the error up until a certain point. And then from that point onwards, making the model more complex is hard. The idea is, okay, how to define this, but there is such a point. This is actually as simple as this is, it really captures most of the thing that we do in machine learning. Okay. We talked about the linear version of the problem. Now let's go to the classification problem. In the classification problem, unlike the regression problem, the Y is not continuous numerical. Instead, the Y is the category, is the class, color, gender, whatever. These are just classes. So predicting whether an individual will default on his or her credit based on income, monthly credit card balance is a classification problem because the output is one of the two. Whether the person will default or not. So in this case, to predict whether the person default is Y, and our X1 and X2 are just our income and the balance on the monthly balance on the credit. So just to give you the picture of the problem, it's still a 3-dimension because you have income, you have balance, and then you have the class itself. So we are showing the default with the pluses, I guess, and the non-defaults with the circles. And these are the charts that we draw a lot, the box plots that we draw a lot in the previous courses. They are looking at default yes or no on the x-axis, and the distribution of balance on the credit card or the income. So just going by simple looking, it looks like that the balance on the monthly balance on the credit card plays a huge role in finding whether the person would default or not. Income plays a lesser role. Okay. Another example is that even a possible outcome for a medical condition is stroke, drug overdose, or epileptic seizure. So 3 classes. And we are trying to predict whether that person would be in any of these 1, 2, 3 situations, given the predictors that we have. The reason that it's kind of clear, but the reason that we are not using, even though we put 1, 2, 3, it doesn't, there's no ordinal value. It's just the label of that class. So we cannot use linear regression because we are not trying to predict 1, 2, 3. Again, 1 is smaller than 2, 2 is smaller than 3. But there's no such a notion between these 3 classes for us. We're trying to predict whether the person would have a seizure or stroke or a drug overdose. For these type of problems, the simple version of the regression is the logistic regression. And let's see what it does. So there is a fundamental difference between how we solve this and how we used to solve the previous problem. go back to the default on the credit card example. And this is very important to understand. I think I've emphasized this before, but I'm going to emphasize again. In the logistic regression problem, let's say we only have balance again. We are trying to predict. The ultimate goal is to find whether the person would default given the balance, okay? But what we do instead is to find the probability. Find the probability that the person would default or not, given a variable. It is hugely different than what we were doing before. Before that, we were trying to exactly predict some number, house price or whatever. Here, we're trying to predict the probability. And then it's easy to get from a probability to a number, right? If probability is more than 50%, go with default, otherwise go with non-default. But the good thing here is that the probability of 51% gives you a different confidence than a probability of 88% or 99%. But the good thing is that in the last layer of a logistic regression, before getting to the actual 0, 1, 2, 3 prediction, you also have a probability of each class, which you have to look at and make a decision based on that. So logistic regression tries to find the probability of Y belonging to a certain class. Okay, what is specific about probability? A probability is a number between 0 and 1. And obviously, if you're solving a binary problem, if you know the probability of 0, you know the probability of 1. Because it's just 1 minus that. Let's think about a binary classification using logistic regression. So we have two classes. Y is either 0 or 1. But again, let's assume we have many features. We have M features and N samples.
Professor?
Yeah.
So what's that equals 1? I have no idea. Like XI.
So this is just, okay, so when we have M feature and a bias. So that's our bias value. We're assuming that our bias is 1. The goal here is to find these W's. So these are the values that we have. So in the example of credit cards, the balance, income, whatnot. The first one is just you assume this is 1.
Oh, okay.
Because you're trying to find the bias. So these are the weights. You have M weights and a bias. So basically the problem is going to W1x1 plus W2x2 plus WMXM plus W0. The intercept of the line in one dimension. Okay. Keep the probability at the back of your mind because we want to get. So think of a linear model back again. If there was no 0 and 1, if you delete this is just exactly the linear regression problem, right? This is exactly the linear regression problem. You have M features, and that gives you a Z. The question is that how do we get from Z to a 0, 1? How do we get from Z, which is a linear regression number, continuous number? Simple way is, okay, if Z is very high, Y is 1. If Z is very low, Y is 0. But it's still, it's not very exact. So Z is very high is not a proper mathematical format. Oh, there is a TV over there. I feel like I'm a candidate, so I can talk in the teleprompter. You see this guy debating? There was a debate last night.
Yesterday,
Yeah, you guys are not watching, right? Good for you. Actually, it's very good that you're not watching. It's very healthy. The GOP debate. The Republican debate for presidential race.
Who is your favorite professor?
I saw one in the past, but these days, if I were to pick one,
Everyone looks toxic, professor. That's the main problem with GOP. Like, Nikki, except Nikki Haley, everyone looks so toxic. That Ramaswamy, that Indian guy, and the
why toxic?
toxic in the sense of the way they. I would say.
So the idea was, okay, we started the linear regression version. The Z is high, map it to 1. The Z is low, map it to 0 is not the best solution. So what can we do? So again, the problem is that we want to find a way to convert Z. This is a linear regression problem, right? All the way to it. It's exactly like linear regression. But we prefer to map it to a 0 to 1. Because then that's a probability and there is a middle point for that. But Z by itself does not have a middle point. How do you convert a number between minus infinity to infinity to a number between 0 and 1?
Sign.
That's one way. That's another. It's called sigmoid or logistic function. It takes a number between minus infinity and infinity and maps it to a number between 0 and 1. So Z can be any number from minus infinity to infinity. For very small Z, this is definitely 0. For very large Z, this is definitely like 1. This is a simple way to convert. But you see, it's not linear, right? Meaning that for very like Z equal to 4, you get all the way to 1. And for Z, you see, you get very quickly to 1 and 0. Okay, so with that, you can simply start with the regression version, find the Z, plug Z into here, and get to a number between 0 and 1. Okay? So just rehearsing the problem. You have a bunch of features and bunch of weights. If you start with the regression problem, you have a number between minus infinity and infinity. You apply the logistic function or sigmoid function on that Z. You convert it to a number between 0 and 1. A number between 0 and 1, now you can consider the probability. Right? And probability is easy, you see. From this point above, you can say this is a 1. From this below this point, you can say this is a 0. But you also have a probability associated with that, which is good. Just repeating the stuff and say where you make your decision. So you can simply still go back and just compute Z. And if Z is larger than 0, say class 1, C is smaller than 0, class 1. The good thing is that the sigmoid function converts Z to a probability for you. And you need that. Looking from a perspective of line, this is Z, right? Z larger than 0, you predict 1. Z smaller than 0, you predict 0. But you also have the probability in between. So a 0.6 is different than a 0.7. Although they are all mapped to 1, you know what confidence you have on those. This is logistic regression. Okay, how do we solve the problem in logistic regression? So it is kind of like, so remember linear regression, I said there is this function. You define the cost function, J. You take the derivative with W and B, and then you do gradient descent and you find the outcome. Here, you have the Z. Right? You apply the sigmoid function on that. So your definition of J is going to be very different. Even though the inference part, the formulation part is very similar to linear regression, you just apply sigmoid function somewhere. The cost function is going to be very different, and I'll explain why. So if you look at the cost function, let me write this here as well, just for the sake of understanding this. So these are the actual Y's, right? The observation. The cost function is again a function of weights. It's forget this part, you average over all the samples. For each sample, you do Y. This is observed or target value, right? It's either a 1 or 0. This is either 1 or 0. Or a binary. Think of binary for now. Log of what is this guy? This is Z, right? This is the sigmoid applied on top of Z, which is basically our Y hat, right? Our prediction. This is not a 0, 1. It's a probability, right? We can convert it to a 0, 1, but it's not a probability. It's not a 0, 1. It's a probability. Minus okay. Can someone tell me what we are doing here? How this is a cost function? And how is this penalizing error? So we know if, let's assume yi is 1. Okay, assume. For a given I, for I equal 3, yi is 1. So remember, this is a probability. It's the output of the sigmoid, right? It is still a probability. So what does it do? Okay, you are, in this case, you are looking for a 1 here, right? You prefer this to be 1. If y hat happened to be exactly 1, luckily, but you know y could be 0.99, 0.6, 0.3, right? Could be any of them. But if y hat was 1, your error is what? It's 0, right? Because this is 1 log of 1 is 0, and this is 1 log of 0 is 1 minus. Okay. But okay. But by the way, if y is 1, this term is anyway 0, right? So if y is 1, all you are dealing with is yi log of y hat, which is 1 times log of y hat. And again, I equal 3. So if this is 0.9 or 0.8 or 0.3, the number is going to be different here. So what it does, it says, I look at for every prediction, I look at the probability, I take the log of it, and I multiply it by 1 if the sample is 1. Which means that the farther my prediction is from 1, the more I'm gonna penalize this in my cost function. If you're just trying to understand what this formula does. Because if you have a 1, 0 system, okay, let me explain this in a different. If you have a 1, 0 function, okay, one way for you is to say, okay, I'm gonna wait for the prediction. If prediction is 1 and the sample is 1, no error. Otherwise, 1 error, 1 unit of error. But what you're saying that let's not penalize every prediction, every wrong prediction equally. Let's actually penalize them based on their probability, which is the output of the sigmoid function. So if for a sample, my model is able to give 0.99, it's very good. Let's penalize it a little. Whereas if it's predicting 0.6, it's kind of very close to the border. Whereas if it's predicting 0.3, it's very bad. But the best function to do this is a log. So this is penalizing the difference between the probability and the expected prediction, which is 1 or 0. Again, if y is 1, all you care about is this term. If y is 0, all you care about is this term. What is done is it says, okay, instead of actually looking at the final prediction, let's look at the probability and take the log. This is called the log loss function. So you see, when it gets to cost function, it becomes very different than linear regression. So it tries to minimize the probability of wrong prediction or maximize the probability of correct prediction. In a way, think about it. Let me give you what it does that could be different. Let's say, and actually I don't know the answer, but let's say you have 2 samples, y1 is 1, and y2 is also 1. Y hat 1 happens to be 0.8, y hat 2 happens to be 0.8. This is one example. The second example is that again, 1, 1. Let's say I have a model that does this. And I have another model that does this. One's better.
Maybe second one.
I guess the first one, but let's see. We have a ChatGPT ourselves. You know that? It was sample. Let's see which one is better. Yeah.
There's a difference in the slide and what you've written here.
What's the difference?
In the second function, it's plus 1 minus yi. And over here, you've put.
Yeah, no, but anyway, in this.
That doesn't change anything.
Yeah, no, that's right. You have to sum. But for every y, either this is 0 or this is so. But you're right. No. Okay, so let's see which one is better. In order to see which one is better, I'm gonna do. I actually have to do the minus, right?
Yeah.
So this is gonna be 0.19 cost. $92 and $60. $25. This is better. This is cost. You want minimum cost. And it kind of was, but hey, you have to write the log function to understand. But what we are doing here is that in terms of and you sum them up. So this is the cost of this is 0.19, the cost is. You prefer better predictions on average. This does a good prediction and a very bad prediction. So you see, but again, I'm just trying to get it, you guys to at least understand what the logistic version does that. Is that you first do exactly as you do in linear regression. You compute W1, X1, W2, X, gives you a number. You convert that number into a probability by applying the sigmoid function. And then to calculate the cost, you take the log of that, which basically says that logistic regression, though you have a 0.5 to threshold, it pays attention. The closer you are to 0.1, the better, 1 or 0, in terms of probability. You're more confident, and that's kind of an example of the cost. Question? I'll get to your weird question later. Yeah, I think there is a meta AI. It's like a chat GPT, but yeah, there is a meta AI.
Which one is better?
Actually,
So,
I think in week 4, we are going to talk about week 4 or 5. And maybe I'll ask the guy who, Said, Dr. Said, to teach you. So in terms of which is better, you have to still again find the metric. What metric you define? So how do you define which is better in terms of what? What type of error it makes, hallucinations. So again, even text models, they have their own metrics. Which, they have some public data sets that they compare against, but still these are very far from like being really be able to compare. But there are now 2 or 3 major versions of. Okay, so now you have a cost function. So you can do gradient descent. The moment that you have a cost function, you have to minimize it. You have to find the optimal point. So what you can do here is that you can, you see, this was y hat. What is y hat is sigmoid on top of z. Z is just WTX. So you can just simply apply gradient descent. You have WI, W1, W2, W3, right? It's a multi-parameter thing. And this is the derivative of W with derivative of J with respect to WI. That's how it looks. Basically, you just plug in all the things here. You take the derivative of this, which is slightly harder, now with respect to WI or WJ. And then you find the optimal. These are again different, you were talking about different type of gradient descent algorithms. It's worth, if you guys are interested, you can look into the blue algorithm. Okay, so you can have more than one class, right? You can have more than one class called multinomial regression or multi-class regression. The idea here is that you can have one class or 2 class or 3 class and all of that. The way normally these are solved, it gets more complicated in terms of explaining the math of it. But think of it is that you start with one class and you treat all the others as the binary class. So you first solve, but you have to iterate. You first start with this. So this is a binary logistic regression for which you have the cost function. You can solve this, update the weights, repeat this until you converge. So you break this into multiple binary logistic regressions. One versus one. Yeah, finished. Okay. question?
Oh, hello. Yeah, hello, Professor. So, how can I get the record? Yeah, because I want to double check this path.
What is the question?
Yeah, I mean, how can I get